Good day, everyone. My name is David Williams, Executive Director of the United States Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Adoption of Clean Energy Technologies, Empirical Evidence. We are grateful to our moderator and speaker, Dr. Govinda Timilsina, and our distinguished panelists for today's timely discussion. First, a little bit about the United States Association for Energy Economics. We are the largest affiliate of the International Association for Energy Economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services you can find on our website at www.usae.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our moderator and speakers. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our panelists, please click the Q&A button at the bottom of your Zoom window and type your question. We've allocated sufficient time at the end of this webinar to address your questions. And now I would like to introduce you to our moderator and speaker, Dr. Govinda Timilsina, Senior Economist at the Research Department of the World Bank. Govinda, over to you.
Thank you very much, Dave. First of all, I'd like to thank you for inviting me and the panel to discuss about a very important topic, adoption of clean technologies. Today we have 3 speakers. We have Shanjun Lee from Cornell University. We have a Hochman professor from the Rutgers University, and myself from the Research Department of the World Bank. So first of all, Shanjun will speak about the case of China, where he will be talking about the adoption of electric vehicle. Gal will be talking about the case of US Midwest, where he will be talking about the adoption of renewable energy technologies. Then I will talk about a review of empirical literature, what the literature is saying about the adoption of clean technologies. With this, I'd like to invite Shanjun to present his case.
All right, thanks everyone for joining, and thanks for the opportunity to present this work with colleagues from China Automotive Technology and Research Center, Cornell, and the World Bank. So the future of transportation is electric. The combination of an electric vehicle fleet and renewable energy present a great potential to fight climate change. After about a decade of market development, the worldwide sales of electric vehicles reached over 2 million units in 2019, accounting for about 2.5% of market share of new vehicle sales. So China had a sale of over 1 million units, about 50% of all EVs sold worldwide. The United States represented in green here, and European countries represented in red, accounted for about 15 to 20% of EVs sold worldwide. So in terms of the market share of EVs in the new vehicle market, country by country, Norway has by far the highest market share of about 56%. That is, out of 100 new vehicles sold in 2019, 56 of them were electric vehicles, 15% in Netherlands, 11% in Sweden, about 5% in China, and 2% in the United States. So in terms of the charging infrastructure, China had, by end of 2019, China had over 500,000 charging ports or charging outlets, followed by US and the Netherlands. The US and China have very different market structure in terms of the production of electric vehicles. In the US, there are about a dozen EV automakers or EV producers. with about 50 EV models. So Tesla had a market share of over 50%, followed by Chevy, Toyota, BMW, Honda. But in China, there are about 70 automakers that produce EVs and about 200 EV models. BYD is the largest automaker in China, had a market share of about 20%, followed by Beijing Auto and Shanghai Auto. So there are at least 3 reasons or rationales for policy intervention for government to step in to intervene in this electric vehicle market. The first is there is a suboptimal gasoline tax to correct for externalities associated with gasoline consumption, such as air pollution and carbon emissions. Second is there might be consumer misperception of future fuel cost. As a result, consumers may not take up cost-effective investment. There's a large literature on energy paradox. The third reason is that there are technology and consumption spillovers in the production and demand side of the EV market. So EV producers cannot appropriate all the benefit from R&D investment, and consumers cannot appropriate all the benefit from adopting EVs because there is indirect network effect on the demand side. So the indirect network effect captures the interaction, the interplay between charging infrastructure and the EV purchase. So as a result, without any government intervention, there might be inefficient, low levels of technology investment in the supply side and consumer demand in the demand side of this EV market. So if you look at incentives provided, there are 2 broad categories: financial incentives for EV adoption and non-financial incentives. So in the United States, there is federal consumer subsidies that are based on battery capacity. A key difference from that is China provides a subsidy based on driving range, which could lead to different results. And in addition to the federal or central level subsidies, there are also subsidies from local governments. So let's focus on China's central subsidies from 2013 to 2018. In 2013, a consumer can get about $5,000 US or 35 yuan subsidy for buying an EV that has a range larger than 80 kilometers. Over time, the subsidy has reduced and the range requirement has increased for battery electric vehicles. For plug-in hybrid electric vehicles, the range has been at least 50 kilometers and the subsidy has decreased over time. And the subsidies were scheduled to phase out in 2020 this year, but due to the pandemic, they are extended to 2022. Now, at the local level, there are financial incentives. The local government provide consumer subsidies that often tie to central subsidy. There are also non-financial incentives. For example, preferential treatment for EV buyers. In many Chinese cities, in order to address traffic congestion, the cities adopt a quota system for vehicle purchase to limit the new vehicle sales. And many of the cities gave EVs exemption. And then there are similarly road access privilege for electric vehicles. Another interesting policy is a green plate policy. So EV buyers can get a distinctive looking license plate that can show others on the road that you are driving an electric vehicle. So in this study, we are trying to understand the driving factors behind the rapid growth of the Chinese EV market. And we want to quantify the impacts of different policies on sales of electric vehicles. We have very detailed data. This is sales data. These are sales data by city, by vehicle model, by quarter. From 2015 to 2018, there are about 190 unique models. These are nameplate by driving range combinations. We focus on 150 cities, including top 40 cities with the largest EV sales and their neighboring cities. In total, these 150 cities account for 78% of national EV sales during our sample period. We also collect very detailed local financial and non-financial policies in these cities. So this shows you sales per million residents in 2015 on the left and 2018 on the right. You can see there is a dramatic increase over time, but also you can also see a very strong spatial heterogeneity, even among neighboring cities. So what we are going to do is we are going to compare sales in neighboring cities of the same model during the same time period, and try to examine the differences in policies across neighboring cities on the sales of EVs. The underlying assumption is that because these neighboring cities tend to have very similar observed demographics, such as income, we assume their unobserved demand shocks are similar as well. So the empirical framework is a linear regression with panel data. We have sales of a model K in city C at time T, that's year quarter T, on the left-hand side. On the right-hand side, we are interested in the impact of price P on sales. Price is after subsidy price, and is number of charging stations in the city at a given time T, and two policy variables. Those are driving exemption from driving restrictions, DR, and green plate policy. We also have other vehicle attributes in X and a rich set of fixed effects to control for unobserved demand shocks. So in order to establish the causal impacts of subsidies, charging infrastructure, and other policies, we have to address the potential endogenities in P, in N, in those policy variables. We use instrumental variable methods and this city border design, for which we don't have time to go into. This shows the results from auto-release square and also from the IV results. You can see the coefficients in the first one, that's coefficient on consumer price, changed quite a bit after we use the instrumental variable method. That illustrate the importance of controlling for the endogeneity. The results are quite robust across a range of function specifications and sample selection. And this basically these are simulation results based on our parameter estimates. We remove one policy at a time. By removing the subsidies, central local subsidies during our sample period, the sales of EVs would have been 45%, represented by the blue line here. By removing the green plate policy, the sales would have been 82% of what we observe in the data. So the results suggest a subsidy of 10,000 yuan, that's about $1,500, increased EV sales by nearly 16%. And the total consumer subsidy from central and local government explain about 50% of EVs sold during this period. And interestingly, an increase of 1,000 charging ports in a city increased EV sales by 20%. Based on the cost of a charging infrastructure, we find that investing in charging infrastructure is nearly 4 times as effective as consumer subsidies in promoting EV sales during our sample period. Lastly, green plate policy contribute to nearly 18% of EV sales. This highlights important psychological and social dimensions of the diffusion of environmental friendly technologies. To conclude, we found that government policies played a crucial role in rapid growth of the EV market in China. Generous consumer subsidies from both central and local governments explained at least half the EV sold during this sample period. However, we found subsidizing charging infrastructure would have been much more cost effective than subsidizing EV purchase. Lastly, the green plate policy, although has a very small cost, was surprisingly effective, pointing to conspicuous consumption of green goods that has been documented in other contexts. Thanks very much.
Thank you very much, Shanjun. Very interesting presentation, and thank you for keeping the time. Our next speaker is Hochman. While Gal is sharing his slides, I'd like to request the participant to hold their questions until the Q&A session. We have a 15 minutes Q&A session at the end of the third presentation. Gal, your turn.
Hi, good morning. This talk is about a paper written by Zisong, which did most of the empirical analysis, and myself. It is about understanding the competition in the electricity market and the implication to the adoption of renewables. Evidence is from the RGGI, the Regional Greenhouse Gas Initiative, which is an initiative in the Northeast and Mid-Atlantic region. So the Regional Greenhouse Initiative is an environmental program that is located in the Northeast. Initially, it included 7 states, and the focus of this study is mostly on the announcement and how it impacted electricity and adoption of renewable generating technologies following the announcement, which was done at the end of 2005. It includes more than 7 states, 3 joined shortly afterwards, and more are now contemplating of joining this initiative. It's a mandatory program aimed at reducing emission of CO2. It is built on a cap, and an aggregate cap on CO2, and there's an auction for the pollution permits and the trading of those permits among the parties, the stakeholders. What is interesting and what resulted in us working in this region is that parallel to RGGI, there's the electricity markets. The electricity markets are the outcome of the Federal Energy Regulatory Commission order number 636, which broke and defined wholesale markets that are responsible on monitoring and transmission of the electricity generated to the end users. That wholesale market has been defined through independent system operators and regional transmission organizations, which are very similar today. The size, the spatial size of them is what makes them different. And that's where a wholesale price is determined. They coordinate the transmission and monitoring it on the interstate electricity grid. Different than the wholesale price, you have the retail markets. And the retail markets are much heavily regulated at the state level, and they involve the sales of electricity to the end users, to the consumers. Now, when looking at those regions, so 3 of those regions are actually where RGGI is. So you have an environmental policy that is affecting 3 different electricity markets. But what is more interesting is that one of those electricity markets, some of the states are under the regulatory framework, whereas others are not. And that allowed us to use a different approach to try to understand how did environmental regulation impact the adoption of renewables? What impact did it have on the use and adoption of that technology? Specifically, if you look at RGGI includes this region where the PJM interconnection is where you have 3 states that are part of the RGGI announcement in the end of 2005, which is in New Jersey, Delaware, and Maryland. And then you have the other states which are not not announcing they're willing to join RGGI at that point, although some of them are now thinking of it. That, again, introduced us to this ability to apply this approach, a different approach, and I'll be more specific in a minute. Just to understand when we look at the electricity prices, because we want to understand how did the market respond to this regulatory framework. So we have a wholesale price that is determined at these ISOs or regions, electricity markets. That price usually is composed of 3 elements: the energy price, the price of generating the electricity, the congestion cost, and there's a cost of marginal losses. During the period that we are investigating, PJM did not report the 3 separate costs. It only reported an aggregate cost, and therefore we focus on the total cost. More than that, the way the markets are structured, it's it's competitive, it is hourly and sometimes even every 15 minutes. However, we'll need to aggregate it, as I'll be more specific in a minute. On the other hand, you have the retail price, which is the wholesale price plus fees. This is a less frequent volatile price. It is fixed over a longer period of time, monthly and annually, and again, it is much more regulated. So just to understand the electricity price, because we're going to focus a lot about it and understand how did regulation affect electricity prices, both at the wholesale and the retail prices, and then how did that percolate into the adoption and impact on investment in renewables. So when we look at the electricity price, about a third of the price, the retail price, is coming from the wholesale price. However, there is a big part that is not coming from the wholesale price that is related to delivery, about 45%, and then there's taxes, 15%, and purchasing costs, which is another 5%. So a big part of the retail price is not the wholesale price, it is associated with the fees. And we were interested to understand how did the fees respond to the introduction of regulation and the infrastructure investment that followed that. To use this structure that is built on two mechanisms, one is the electricity markets, the three electricity markets, and the other one is the regulatory environment, the environmental regulation. We start with PJM. The PJM region has, as we said before, 3 states that are part of RGGI, that are announcing the implementation of a regulatory environment, regulatory policy that is going to take into effect in 2009. And then there are other non-RGGI states. We chose 2 neighboring states, Pennsylvania and Virginia. They're bordering New Jersey and Delaware, and that is to keep things as controlled as possible. These are neighboring states. All states are unregulated. However, it should be noted, and I'll show you in a minute, if we go to the full sample, we see similar results. The result did not change as you add the other non-RGGI states that are part of PJM. We should remember that the wholesale price is defined as the total wholesale price, all 3 components. It is aggregated daily at the state level because to reduce the noise in the data. And again, the focus is from the beginning of 2005 till the end of 2006, where the event that we're interested in, the announcement and how it triggered change, is the end of 2005. It's the end of December 2005. That's when the announcement of RGGI came in. On the other hand, you have the retail prices. They're at the state level that came from the EA. That data is much less, much more aggregated, less frequent. So we use the longer period just to kind of understand how did these prices interact again, so we can understand how did they impact the adoption of renewables. How did prices react? On the left side, you see the annual wholesale price. And as you can see, the announcement of RGGI did not really have a big impact. This graph is plotting the 5 states. 3 are RGGI members, 2 are not. All 5 of them are part of PJM. And you can see that when you look at the wholesale price, if anything, the price have been pushed down over time, but there's no big change between RGGI and non-RGGI states. This is very, very different than what we see in the retail prices. When we look at the retail prices, the red line is simply the event date. When we look at the retail prices, the top 3 lines are the RGGI states. The bottom 2 are the non-RGGI states. So we do see a very strong push, and you can see also the steep hike in prices, in retail prices that came following the announcement of RGGI, which actually peaked at the time that RGGI implementation has begun in those states. And the question is, why is that happening? Is it because infrastructure and investment in renewables, such as solar and wind, picked up and there was a need to support those utility companies and the transition that they're trying to make? Or is it driven by other factors or other components? Just quickly, this on the left here, we just plot all of the states, all states that are part of PJM. The top line again belong to RGGI states, the bottom one are non-RGGI states. And statistically we can show, I'll just go quickly over it, we show it the same thing. So the framework and the way everything is structured allowed us, allowed Z actually, to implement a diff approach in a very clean way. And when doing so, she controlled for various variables from natural gas price to population to GDP. She also introduced lags, first, second, and seventh, following Contreras that showed that these three lags are important. And what we're interested is in the diff of diff. It's the first line. And when we wanted to choose, so she ran several models to understand the robustness of the results. And we used two criterions to decide what model are we going to implement. One is the parsimonious principle, and that is if you have two nested model, you'll choose the and the model that is nested within the more detailed one has a similar explanatory power, you will prefer the model with the less control. The second one is coming from Angrist and Pisquet 2008, and that is the idea of the bracketing property, because you can't simply introduce state time fixed effect as well as lags. You create a bias in your estimates. So what they proposed, and we adopted that approach, is that you run two different regression. You create a bracket, a lower and an upper bound to your estimates. One is controlling for the state and for the fixed effect. In our case, it's the state and time. And the other one is the lag that is introduced when you don't introduce the fixed effect of state, because that creates the bias. These two estimates introduce a bracket, an upper and a lower bound of our estimates. So again, she ran many robustness checks and analysis and tried to refine it and understand the magnitude. And the outcome is very interesting because, first of all, when we look at wholesale price, if anything, the announcement of RGGI resulted in prices going down. And again, these are two models picked based on the parsimonious principle and the bracketing property. So we get this range of negative prices reduced because of the announcement of RGGI, and we can show that trend actually has been maintained over time, even as we moved into the implementation of RGGI and later on. This is very, very different than what we see when we look at the retail prices. The retail prices, again, applying the same techniques, the same bracketing property and the parsimonious principle and taking the robustness over many models and various specification and various control variables, we get prices has increased, and this is actually significant. When we look at the wholesale prices, it is not statistically significant, although it is negative. In the retail prices, it is very significant and it's very substantial. And the question is, why is this happening? Is this happening because of renewables? Or is this happening because of investment? Or is this happening because of something else? And I'll comment, I'll try to end my talk as quickly as possible. So when we look at infrastructure investment and adoption of renewables, we do see a very different pattern when we look at RGGI states. This is the rectangle that is marking them. So you can see the announcement is the upward sloping line. These are RGGI states. The dashed lines are solar and wind. And you can see that there is a spike, a substantial increase as you reach the announcement. New York is a bit of an outlier, and as is New Hampshire. But overall, you do see this correlation, and we can measure that correlation. This is very different than what we see when we look at non-RGGI state. And if we add the others, you see it even more so. So the question is, what is happening? We use data on CompStat. We can have exact data on renewables, but we do have data, from labor data on total infrastructure investments, or investments, sorry. We can explain with it about 30% of the gap. So that means that the gap between the retail and the wholesale prices, which is driven by the price that the state are setting, given the wholesale prices, and the fees that they're collecting and then using it to support the utility companies, is significantly higher than what is required by the infrastructure. I won't go too much into it. You do see a very different patterns of investment when we look at RGGI, which is the figure on the left, versus non-RGGI, which is the figure on the right. You do see an increase in fees that is not that is impacted by infrastructure, but there's something else going on there. We don't think it is. We do think, okay, so we do suspect, and I don't have it here, but we do suspect that some of it is driven by the public debate and the concern for higher electricity generation that resulted politically in a driver and a justification for pouring more money into the utility companies. We can conclude it is not, there's no problem with leakages or other problems there. And more than that, the RPS is not able to explain this phenomenon that we are alluding. As important as it is in promoting renewables, as we saw in the previous talk, we do think RGGI caused these differences and these differences in prices, but we also think that not all of it can be justified by the need to make investments that increase adoption of renewables, which we did see follow. But just one more comment and I'm done. It's important to understand that RGGI also resulted in an increase in natural gas prices. However, statistically, we cannot rule that we also saw some increase in renewables because of the policy. So RGGI more than that caused coal to be more expensive and natural gas to be favorable, but it also resulted in renewables such as solar and wind being adopted in RGGI states. Thank you very much.
Thank you, Gol. Very interesting technical paper. You might have some questions, but so we have to wait until the Q&A session. So now it's my turn. So I'm going to present. Okay. So Shanjun speak about electric vehicles in China. Gol talk about renewable energy technologies in US. So I will be talking about clean cooking from the developing country perspective, bringing the knowledge from the existing literature. So this presentation based on a paper, so we published in an IAEE journal, Economics of Energy and Environmental Policy. And Sunil Malla, who might have participated in this webinar, was a co-author of this of that paper. So why clean cooking is important? So if we see the energy consumption in a household sector, we can see that there is a huge portion of the energy consumption in the household sector is still coming from biomass. So yeah, so I cannot see in my screen here, but that's fine. So what is happening in 1990, about 42% of total household energy consumption is a total household energy consumption, not only cooking energy consumption, coming from biomass globally. Now it's about still 35% of that total household energy consumption is coming from biomass. That shows how important it is. And in South Asia, particularly in India and Sub-Saharan Africa, they're still relying on biomass for meeting their household energy demand, particularly for cooking. However, there is some negative implication of the huge application of the biomass in cooking in the household sector. The World Health Organization estimates more than 4 million premature deaths annually, and mostly women and children, due to household air pollution, which is mainly coming from burning of solid biomass. And most of the impact is occurring in Sub-Saharan Africa and South Asia, and particularly in low-income households. This shows how important the clean cooking is. Also, there is some environmental implication of biomass burning. It is one of the sources of deforestation in Sub-Saharan Africa, and there is a visible evidence in mountain region in South Asia that so it is causing deforestation in that region. Biomass burning is also the main sources of black carbon, and black carbon is a primary culprit for climate change impact in the Himalayas, for melting glaciers and melting the snow covers. So considering this adverse impact of biomass burning, and also there is a health benefits, environmental benefits of switching over to the clean cooking, a lot of efforts have been made over the last 40 years. Governments, international development institutions, bilateral donor agencies, non-governmental organizations, they are all working continuously for promoting clean cooking all over the world, in developing countries, particularly low-income countries. There are hundreds of programs on clean cooking stoves and also other clean fuels at the national level and also at the regional levels. Various support schemes have been developed. For example, free distribution of the clean cooking stoves or improved cooking stoves, heavy subsidization of the clean cooking fuel, particularly LPG, awareness campaign, and many other initiatives. Despite this strong promotional campaign and also huge benefit, including the environmental and health benefits, which is much higher than its cost, the adoption of clean cooking is still slow. And the question is why? So in this presentation, I'm going through the literature, existing literature, which is basically published journal articles, and trying to understand what they found. So what are the main factors that is hindering a rapid scaling of clean cooking in developing countries? There are many factors. We can identify so many factors. However, we can group them in these 6 categories. First one is the supply factors. That means clean cooking devices or fuel is not available. That's why there is no adoption. Economic factors, basically affordability. The initial cost is normally high of the clean cooking devices. There is no systematic provision for financing. Consumer has to pay at the very beginning all the initial costs. That's why it's difficult to afford it. And obviously the income is the main factors. Social factors. There is a lack of awareness of existing of the clean cooking devices and fuels in many remote and rural areas. Household, they do not know the knowledge about the indoor air pollution, how much the indoor air pollution is causing adverse health impact to them. That means a clear lack of knowledge. There are also technological factors. The devices are not necessarily as reliable as they are supposed to be. They malfunction before the design lifetime. Once malfunction, the maintenance is not available. And there is also mismatch between the devices and the kitchen. It requires remodeling of the kitchen, which is expensive. Behavior factors. Even if there is no supply issue, there is no supply constraint, even if people know there is a huge benefit of having clean cooking practices, fuels, or devices, still it's a human behavior. They are ignorant. It's like smoking is dangerous, but still people smoke. So there is institutional factors. Basically, clean cooking is promoted through the incentives, and the institutional capacity across the country is different. Some countries have a good institutional capacity. They have a good policies, while other countries did not have it. So one question is that how important these factors are? These factors are equally important, or some factors are more important than others? So there are huge literature. They're using empirical studies. They're doing the surveys, analyzing the data, and coming to a conclusion. So many studies shows that a factor, the economic factors and the knowledge factor, the level of education, the gender of the household head, and obviously the income level is the main factor that is delaying or that is slowing the adoption of clean cooking. There are many studies providing evidence of it. There are studies in India, in many countries in sub-Saharan Africa, in Afghanistan, in Latin America like Guatemala and Peru. So those studies are telling, a large number of the studies are telling that the level of education, I mean the level of information grasping capacity, the gender, and the income is the main factor for slow adoption of clean cooking. Then also there's literature that saying that the behavior factor is also important factor. Studies in India and also in Latin America and some countries in sub-Saharan Africa telling that although income is, even if the income is not a problem, they can afford for it, even if supply is available, but still households are not adopting clean cooking because of the behavior factor. For example, the taste of wood stove, I mean barbecue, a taste of a meat baked in a barbecued in the cookie stove is much tastier than in the LPG stove or even clean cooking stoves, wood stoves. So high income population, they might still use the traditional stove because of a taste reason, the food taste reason, and also cooking habit. Some studies are telling, but not that many, about the institutional factors, the lack of support policies, for example, a study in Kenya. A supply factor is obviously the reason, but not that many papers are talking about it. If there is no infrastructure, obviously, this is an obvious question that there would be not much adoption of clean cooking. And some studies are also talking about the technological factor. There is a study in China. Not necessarily these are the only study. There are many more studies. I'm just picking some selective studies. So which trying to identify what are the main barriers, what are the main factors that are causing a slow adoption of clean cooking in developing countries. So what is the key policy message? Despite the global promotional efforts over the last 4 decades, adoption of clean cooking has remained slow. This is the fact, observed fact. Several factors are responsible for the slow adoption. The existing empirical studies suggest that 3 factors, cost or affordability, the knowledge, and the behavior factor are the most prominent ones based on the existing studies. Therefore, policies should not equally treat all the factors. Instead, policies should be designed addressing the most important factors. For example, to address the information, there should be information campaign through school curriculum on indoor air pollution and clean cooking solutions. Subsidies is a most common incentive or policies. However, subsidies sometimes, in many cases, benefit those who can pay for it, the rich household. That's why the general subsidies is not the solution to promote the clean cooking or even the other clean technologies. Instead, a targeted subsidy would be more effective. Targeted only to the low-income household would be effective to promote clean cooking, particularly in the low-income households. And the community-based programs with the capacity building, normally what happens that when the donor agency go to the developing country, they implement a project. Once they leave the project, then project gradually dies because there is no constant support for the project. Instead of having this type of one-time shot, what would be more sustainable is community-based programs where the clean cooking program should be communicated, should be provided to the community. The capacity of the community is improved. Ownership, they should have a ownership. They should have a clear understanding the benefits of the clean cooking, and they can run the program by themselves. with some constant monitoring of clean cooking for the long time. So that might be more sustainable approach to promote the clean cooking. And also the integrated approach. So we can see many programs are going in parallel. For example, clean water and hygiene program, vaccination program, and many others programs in separately. Instead of that separate programs, because they are going separately because of the different line agencies are responsible to implement them. Maybe the government and the international organizations should work to have a more integrated programs where all these elements can be put together and then communicated to the community so that they can implement more effectively. So with this, I'd like to stop my presentation here. Next, we have a question and answer session. I'll request Dave William of USAEE to handle this question and answer session. Dave, see you now.
Thank you, Govinda. Thank you to all of our distinguished speakers for this session. I know I've personally learned quite a bit. This is the Q&A time. So for those of you that are listening, we would ask that you type your questions into Zoom. Just take the link down at the bottom. I'm not seeing any in at this particular time. But we've got a few moments for people to enter these. Govinda, I would ask you perhaps, do you have specific questions that you would like to put to your panelists?
Yeah.
At the same time, for our panelists, there might be a question that you heard from the presentations that would stimulate dialogue.
Sure. I do have a question for both Shanjun and Gaul. Shanjun, so what is the big challenge, to further expand the EV in China? And for Gaul, do you have any idea or thought how much REGI helped to expand the market for clean technologies in those states?
Yeah, so Govinda, yeah, that's a good question. I think although electric vehicles is much more expensive, much bigger thing than the cooking stoves, I think the reasons of kind of slow penetration, not only in China but worldwide, some of them are quite similar to what you've talked about. For example, the cost issue. Electric vehicles are still quite a bit more expensive than gasoline vehicles. Even if you factor into the gasoline prices, a few cost in the long run, because the battery is still quite expensive. Although the cost has come down quite a bit in the past, 5 to 10 years, but still not quite to the level needed. For example, it's about $120 per kilowatt hour in terms of battery capacity in order for EVs to be competitive with internal combustion engine vehicles. Right now, the cost, I think, is still about 160 or even higher per kilowatt hour. So there are other reasons, of course. There is the range anxiety issue, the lack of charging infrastructure. In the US, we have about, I think, 25,000 charging sites, charging stations, but we have over 100,000 gasoline stations. So the charging infrastructure is still an issue in the US and in many other countries, even in China, although China has now over 50,000 charging sites and over 500,000 charging ports. But still, most of them are actually concentrated in only top 10 provinces. So the coverage is a big issue. So there's also consumer awareness, as you mentioned as well, for cooking stoves. So those are really the common challenges for the adoption of new technology.
Thank you.
Reggie was a facilitator. I think he came into being in states that wanted to move to green technologies. I also think that one of the reasons the retail price is significantly higher than what is needed to fund the infrastructure is to create a benefit and to help the transition. You're asking utility companies to switch and you're asking all industries, incumbent industries, to face competition from new renewables. And I think that's what was driven, that is part of it, the political component that was driving the increase in prices. Having said that, renewables, if you look at the renewables, their percentages increased significantly. This is data from the EIA. In terms of total consumption, renewables are still small in the region. But if you look at how much wind was in 2004 and how much wind was in 2008, you do see a significant increase. If you look at how much wind do you have relative to coal and natural gas, it is small. So it depends how you're measuring the number.
Okay, thank you. David, you are
come off of mute here. Gul, there has been another question that's come in regarding RGGI. This one for you from Charles Mason. One would expect arrangements like RGGI would be expected to raise cost of producing electricity. What factors do you think explain the negative effect you have found? Is there some subtle iteration with other regulatory agencies at play here?
I can only speculate. When you look at wind, the marginal cost of producing electricity from wind once the turbine is up and running is very low. The same as solar. Now, if you look at the competitive market, they're determining the marginal price as opposed to the levelized cost. That's where the retail price that's why the retail price is significantly higher, because it is supposed to cover that infrastructure investments. I think that can explain, and I think that is something that we're actually exploring, because there is this perception that renewables increase prices. However, when you look at the marginal price of generating the extra megawatt using a wind turbine as opposed to using coal or natural gas, wind is simple. It's simply when you have the wind, you get the electricity. It's not costly at the margin, but you do have the investment. So there's a difference between the marginal cost and the levelized cost. The marginal cost, I think, is what's driving these PJM and ISO's markets, electricity wholesale markets. I think.
Very good.
That's what I understand.
Very good. Thank you, Gul. Shanjun, there's a question here for you. Are there peer effects among cities adopting EVs, and thus the sales are impacted?
Yeah, so this is a good question. So we compare neighboring cities in our research design. So one might worry that consumer demand in one city could spill over to other cities. So that's a good question. That's a possibility. So these cities are big cities, right? These are large in terms of geography. So that hopefully could reduce the spillover a little bit. But I agree that's an issue. We do I only showed 2 specifications where we rely on kind of this city border design. We have other specifications where we do not rely on the city border design. So I think that concern is I think it's an issue that we need to look into. Yeah.
Thank you. Thank you. Govinda, question for you. How important is electricity generated through renewables used for cooking in sub-Saharan Africa and Southeast Asia?
That's a very interesting question. What is interesting, and it's a tricky question. So when people say electricity, I mean, it doesn't matter whether electricity is generated from the renewable or electricity generated from anything else. So what is important that electricity is a clean fuel for cooking, and it's getting more and more popular in many countries because its price is coming down. Particularly, even in Asia, in some of the places they have it after the this induction stove. So there's a very clear cost and benefit calculation which is showing that electric cooking is cheaper compared to the other means of cooking. Now, whether it's renewable or non-renewable, that's the different issue. For example, if the renewable is a grid connected, obviously that will contribute to the cooking like other electricity. Now, if the renewable is not grid connected, but the off-grid connected, still there are some technological issues. Whether there's also research is being done if off-grid electricity can be used directly for cooking. There's some experimental work, but I don't think there's any commercial scale economics coming behind it. But otherwise, electricity is, again, it depends where we are talking about. In sub-Saharan Africa, electricity is relatively expensive for many other regions, institutional regions and other regions. And whether it will be really, it can compete with the biomass, maybe not, because biomass basically, available at no market cost, although there is a, cost of opportunity cost involved. It's a tough one, but in some other countries where electricity is coming from hydro or cheaper sources, so certainly it is becoming a competitive source for cooking.
Very good. Thank you. This is a general question for all of you. Gal, maybe you want to start with this. Wholesale prices are driven by marginal costs, which are close to zero for renewable. So the reduction is not surprising. How are investments rewarded in RGGI?
I'm not sure I understand. What do you mean, how investments are rewarded?
This is, I've read it verbatim. I'll say it again. Wholesale prices are driven by marginal costs.
There's a need for investment. Now, part of this investment is for changing the infrastructure to renewable. The other part is that the infrastructure of electricity in this region is old. And as you remember, Sandy came and it was bad. It was really bad. We just had another one actually hit very hard in my township. And again, no electricity for 5 days. And so a lot of the investment is actually to upgrade the current infrastructure system and infrastructure and help it be more resilient to these storms that are coming. And the other part is intended to support the renewable component. I'm not sure if that's what he asked, but that's why.
Well, okay, so Bruno, if you're listening to this and you have a further question, please don't hesitate to chime in now. That's all we have in our queue. We'll give Bruno just another moment if he's got something to add. Govinda, would you like to say some closing remarks?
Yeah, before closing remark, maybe I'd like to address the question, you just had, to Gal and to all of. So the issue here is that whether, there are two issues. One issue is that, the price in a competitive market obviously reflects the marginal cost. But also what happens is that there are two types of cost. One is the energy cost and there is a capacity cost. So basically the capacity cost, the investment is, recuperated through the capacity charges, which is separately, which, capacity market. And here, if we are talking about only energy, the wind has a, because, there is a zero marginal cost and wind is the cheapest one. But at the same time, since wind cannot provide, firm capacity requirement, we need some other generation, ready to run if there is no wind blow or there is no sunshine. So in that case, the capacity is still to be expanded and somebody has to pay, for that capacity. And normally, through the capacity payment, so that cost will be covered. So regarding the closing session, I think it's a very interesting session. We have a very good two presentation. I cannot judge my presentation, so I will let the audience judge my presentation. But it's very interesting and it's interactive. The topic is very important, and what I really appreciate the IAEE and USAE during this COVID time. So you are keeping is very live and very dynamic, having this series of webinar. And honestly speaking, we are benefiting from this regular series of webinar than the IAEA conferences. So that. So thank you very much, and keep it on. Dave.
Good. Thank you, Govinda. Thank you all very much for your time and your expertise. For those of you that are listening, or for your colleagues, this webinar has been recorded. Will be available in open access format on USAE's website, most likely within the coming hours. Thank you all once again. I wish you a good rest of the day or evening, wherever this does find you. And now I officially close this webinar. Bye now.
Thank you very much.
Bye-bye.
Thanks.